All right, howdy folks. Here we're going to go over a reaction sequence. And in this particular case, we're going to use a lot of functional group interconversions to convert the ester starting material into some other functional group way down here. So here we'll just label this our ester functional group. So right there, that's the key piece. Of course, there's this dangling aromatic bit, but looking at a number of the reactions that go through this sequence, I'm sure most of the reactivity will initiate where that ester is. So as is typical for these, what I'll encourage you to do is to first try this on your own. So again, please click the pause button right now. Take a few minutes to try to fill out each of these independent reactions. Try to check your answer and make sure you're comfortable with it before you tune back in, and then go ahead and click play, and we'll discuss not only the correct answers, but also some of the other things that you might consider. Okay, click pause. Okay, hopefully you're coming back now. And what that means is we can go ahead and start with the first reaction. What I like to do initially is identify each of these reactions as the type of reagent they are. And in this case, lithium aluminum hydride, which is our first reagent, is quite a powerful reducing agent. And I typically joke that it's kind of a big sledgehammer, a big kind of clown sledgehammer, and it knocks everything down in oxidation state. And so it's one of the most powerful reducing agents that are typically covered in the Organic 1, Organic 2 class, and it's a very powerful reducing agent. So it will almost always reduce functional groups down. And that's kind of nice because the ester here that we started with is at the +3 oxidation state, and so it's a great candidate to be reduced. And so often when we think about the ester then, we can imagine it being reduced to a number of different conditions. So the first of which would be if it's an aldehyde, we've gone from the +3 to the +2 oxidation state, but we can also imagine it being reduced all the way down to the alcohol at the +1 oxidation state. And in this particular case, lithium aluminum hydride is going to take us all the way. And there are a couple of reasons for that, one of which is it's just a very powerful reducing agent. The second of which is very important, is that the aldehyde tends to be a very electrophilic functional group, and it tends to be much more reactive than esters overall. And so the first box that we're going to fill in then is just going to be the corresponding 3-carbon alcohol. And then if you feel like it, we can also put methanol here, where the methanol comes from that part of the ester. Often that's not a required part of the answer, but it's kind of nice to put it in. Another thing that I'll point out is there's this then acid, and that just represents the acidic workup at the end of the reaction. So after the lithium aluminum hydride has done its strong reduction, often we quench these reactions first with perhaps an alcohol or acetone to consume the rest of the lithium aluminum hydride. Then typically we put in a weak acid of some kind to protonate all the O- that are floating around, and we extract out the neutral alcohol at that stage. Okay, moving on to the second step here, which I'll number with Roman numeral II. This is tosyl chloride and pyridine, and that is a reaction we know to activate an alcohol as the tosylate. And the tosylate we can think about as being a sometimes it's referred to as a pseudohalide, and so OTS is similar to a halogen, a bromide, chloride, or iodide. It has a very similar role, and that is now we've converted the oxygen into a good leaving group. For those of you that have forgotten what the structure of tosyl chloride is, this is TSCl, and so this whole part here is the TS part, and that is then activated as the alcohol. So if we put in our ROH here, we're going to end up making the tosylate. And then we kick off some HCl, and so here's the Cl is from the tosyl chloride part, and then the H plus comes from the alcohol component. And that is what this pyridine is doing right up top. And so pyridine is a weak base. I like to think about it as more of an acid sponge because some strong bases might be powerful enough to actively deprotonate alcohols. Pyridine is a little bit more ambivalent than that, and typically it'll wait around until some strong acid is formed. But pyridine plus HCl, that's the byproduct here, ends up making pyridinium hydrochloride. And it turns out that the pKa of pyridinium hydrochloride is about 5.5. And so it's only slightly less acidic than acetic acid, which is a pKa of about 4.75. And so that's what the pyridine is. And we would make the tosyl chloride. At least in my classes, I'm indifferent if students prefer to abbreviate OTS or if they want to draw out the full functional group. I don't really have a strong opinion there. Okay, so the tert butoxide then, and so remember this is the potassium salt of terbutanol, and this is a strong non-nucleophilic base. Often tosylates are great substrates for SN2 reactions, and that would require a powerful nucleophile. In this case, we're given a base, and specifically a non-nucleophilic base. And so instead of undergoing a substitution reaction, this intermediate should undergo an E2 reaction. And that will generate an alkene. And in this particular case, this alkene has a special name. This is allylbenzene. And where the 3-carbon group here is allyl. So this would be allyl X, whatever X might happen to be. So a little bit of nomenclature there. That's good because alkenes tend to react with elemental halides such as bromine and chlorine to undergo a difunctionalization reaction. And here it's going to be quite important that this reaction is carried out in water as the solvent. And you'll also notice that there's no light given and there's no temperature given. And some of you that get further along might recognize that bromine can also do radical reactions. And here we do have an H that could be removed through an H atom abstraction to generate quite a stable radical. And that's a totally reasonable pathway, but to get into that pathway, you would either need higher temperatures, a radical initiator, or ultraviolet light. And so here the conditions are elemental bromine and water. And so that's an important clue that we're going to go through a bromonium ion formation and open it up with water as a haloform reaction. So the product of that will be this hydroxybromide. And real quick, the way that we're going to get there is by taking our allylbenzene, and we're going to have bromine be attacked. And there's an additional arrow here that I always forget because we're going to make 2 carbon-bromine bonds. And it's this last arrow here is the one that I almost always forget about when making a bromonium ion. All right, and so here's our bromonium ion. Because we have something that's positive now, it's very important to make sure we balance out our mechanism and have a Br minus. And so this would then balance it out as the leaving group. These holonium ions, or in this case specifically bromonium, are often quite electrophilic. And much like epoxides under acidic conditions, they tend to open up at the more acidic or more substituted sites. So again, we could imagine opening here, or we could imagine opening here. And the green side is going to be the more substituted side. And so that should be the side that we're going to end up opening this out. If I carry forward then, we generate this intermediate, and now we're going to take some more water that's in plenty because it's the solvent, and we're going to generate some H3O plus, and that of course is still balanced out by our Br minus, and then the product of that would be the one that I have drawn nice up top. Okay, the last step of the sequence is sodium hydride, and sodium hydride is a very strong base in the form of H minus, and so hydrogen gas has a pKa going to hydride of about 35, and so it's a very powerful base, plenty strong enough base to deprotonate the alcohol in our starting material, and then that is going to undergo an intramolecular SN2 reaction to close this down and make an epoxide. So there you go. After all of these steps, what we've successfully been able to do is to convert this initial ester into the epoxide of allobenzene. Okay, that summarizes this reaction sequence. Again, if you're enjoying these videos or if you're getting use out of them, please do subscribe to the YouTube channel. We're really hoping to get some positive feedback and encouragement to continue making these videos to provide content for all of you who are trying to study organic chemistry. Also, please feel free to follow us on social media or to subscribe as a patron. And when you do that, you'll get access to all the PDFs of these problems and Q&A sheets that I'm generating as part of these videos.